So, welcome back to our lectures on elliptic operators, and today we will try to see what we can get out of, or start to get things out of the functional calculus that we developed last week. So we can now plug in our sectorial operator L into a rather large class of functions, so all regularizable functions. And today we will see some applications of this. So chapter 6 is first applications of functional calculus. And as usual, the first point in the lectures is the standing notation. So for all this chapter 6, again, L will be a sectorial operator in some Hilbert space H. I will again just denote the norm of this space by norms and the scalar products by brackets without index H or something. So if there is a norm without an index, it's the norm in H. And this sectorial operator comes with a sectoriality angle, and this I will, as usual, denote by phi L. Okay. So, and the first application of our functional calculus will be to introduce so-called fractional powers. So, powers of our operators that are of our operator L that are not just integer powers, L squared, L cubed, but that are fractional powers or even complex powers. And as we also want to deal with complex exponents, let's fix from the beginning that we will always work with the principal branch of the logarithm. So whenever you see a complex power, this is defined via exponential and logarithm, and complex exponential function and complex logarithm, and the complex logarithm will always be the principal part, so the argument will be between minus pi and pi. And when you do this, then if you take some complex exponent with a positive real part, then if you take the function z to the alpha as a complex function and you look at the modulus, then this can be controlled by some constant e to the pi modulus of the imaginary part of alpha times modulus of z to the real part of alpha. So what this means is, and this is true for every z in the sector phi, and phi being any angle, so between 0 and pi. So this estimate always goes through, and this means that this complex function z to the alpha has a polynomial limit in 0 and a polynomial control at infinity. So real part of alpha is positive, so for z going to 0, this goes to 0. And in a polynomial way, so there's polynomial control in 0. And this grows in general at infinity, or it grows in infinity, but in a polynomial way, so there's polynomial control at infinity. So this function z to alpha has a polynomial limit in 0 and polynomial control and infinity, and we saw in the last lecture that in this case this is a regularizable function. In our functional calculus, whether L is injective or not, this can be regularized by the regularizer that always works. So this was 518a, which tells us that the function 1 plus z to the minus k is a regularizer for this function z to the alpha if the k is big enough, to compensate for the polynomial growth at infinity. So if the k is larger than the real part of alpha. Okay, and this gives us now the possibility to define fractional powers. So definition 6.2. This means our function z to the alpha is a regularizable function, so we can plug in L. And we just define, so for every exponent with positive real part, we just define L to the alpha as the result that you get if you plug L into this power function. And this is called, these operators are called fractional powers of L. And the name fractional powers is especially made for the case alpha being real and between 0 and 1, but this definition works for every positive real part. Okay, so let's check some elementary properties of these fractional powers. And one obvious question is, if this definition for the powers is the right one, then one should have something like the usual power law. So L to the alpha times L to the beta should be L to the alpha plus beta. And the good news is this works. So if you take two exponents with positive real parts, then you get, as a first thing, L to the alpha, L to the beta is the same as L to the alpha plus beta. And yeah, you can change names, so this is the same as L to the beta plus alpha. Okay. And this is something we have to prove, and we have to prove carefully because all these operators are unbounded operators. It's a regularizable function. It's not a function. It's done for Drie's class. So all these operators come with a domain, and in this equality here in particular means we have to show that the domains are the same. And then there is a second part of this proposition which is about the domains of these operators. So if you take the k large enough to have a regularizer up there, so if you take a k in n that is bigger than the real part of alpha, then I claim that the domain of L of k is a core for the domain of L of alpha, L to the alpha. So it's a subset of the domain of L of alpha, and it's dense in the graph norm. And then, as is often the case, if your operator L is even injective, so if L additionally injective, then we have a second regularizer, a better regularizer at our disposal. So this function z over 1 plus z to the minus 2, z over 1 plus z squared. And then you get a little bit better thing than even the set dom. So the domain of L of k intersected with the range of L of k. So this is a smaller set, and in this case, even this set, this space, is a core for the domain of L to the alpha. Okay. So that's the claim. Let's prove this. So on the side of the functions, this equality is clear. So the functions z of alpha times z to the beta, they have this calculation rule, so now the only question is how to translate it to the operators. And we've seen in 5.15, so we had Theorem 5.9, which told us that the elementary functional calculus is an algebra homomorphism. And 5.15 was the substitute if you are in the extended class. So if you have regularizable functions, then you get unbounded operators and you will not get a true algebra homomorphism because you have to deal with the domains. But somehow 5.15 can be phrased as if everything you write down makes sense, it behaves like an algebra homomorphism. So everything has to be in the right domain, but then everything works out fine. And so what 5.15 tells us here is that if you plug in L, you have two functions that multiply, then you do not get equality here in general, but you get an inclusion. So that was what was formulated in 5.15. You get an inclusion here, and you also know how the domain of the product here looks like. So what is the point that makes it not only an inclusion? So this domain is given as the domain of the operator on the right hand side intersected with the domain of the second factor of the operators. So this was 5.15. And so what does that mean? That does mean we already have one inclusion. We need the other one. And we get the other inclusion if we can show that this domain of the L to the alpha plus beta is contained in this one, because then we can leave this out of the intersection and we get equality. And so the aim is now to show that the domain of L to the alpha plus beta is contained in this one, so that this intersection in fact is only the first one, and then you have equality of domains here, and then these two operators are equal. From a point of view, or heuristic point of view, somehow this makes sense. If you think of integer powers here, if you increase the power, the domain gets smaller and smaller. So alpha plus beta somehow is the real part of this one is bigger than the real part of beta, so this is a higher power, so the domain should be smaller. But we have to check that. And to do this, we take some regularizing function that that regularizes all three of these operators at the same time, and we get this by choosing a k that is bigger than as the real part of alpha and the real part of beta. I don't know, this is not one that regularizes all three, it's one that regularizes the powers with alpha and beta at the same time. Okay, but I take a k that is larger as both real parts. Note that then 2k is larger than the real part of the sum. So this means that the function 1 plus z to the minus k regularizes z to the alpha and z to the beta, and 1 plus z to the minus 2k regularizes z to the alpha plus beta, because then 2k is larger than real part of alpha plus real part of beta. Okay. So now take some u in the domain of L to the alpha plus beta, and we have to show that it's in the domain of L to the beta. Okay, what does it mean to be in the domain of L to the beta? Now we have to go back to the last week, to our regularization. This means that the regularized function, so z to the beta 1 plus z to the minus k, this one applied to L, u, is in the range of the regularizer, so in the range of 1 plus L to the minus k. That was the definition of the domain of a extended functional calculus. And so I will call this element V. So what we have to show is that this V is in the range of that operator. And once we have that, then you can by the regularization procedure, you have V in the domain of the beta power. Okay. Note that we know what this range is. Yeah? This is a resolvent of L. So what is the range of a kth power of the resolvent? This is just the domain of L to the k. So this is the domain of L to the k. So we want to show that this V is in here. We know that the U is in this domain, so somehow to use this knowledge in the calculation that we do now, we have to make appear L to the alpha plus beta. So we have to regularize by a huge amount to make this possible. Oh, huge amount by the right exponent. So what we look at is we take L1 plus L to the minus 1 to the power k, 1 plus L to the minus k applied to V. I want to show that V is in this domain, so this is not immediately clear why this should help me, but the point is I look at this one because this is a regular, you can see this as a regularized version of V, so V is in the domain of, I want to show that V is in the domain of L of k, so if everything goes right, this is in the domain of L of 2k, okay, and this is a bounded operator that I hope will not destroy things, so this will be in the domain of L of 2k, so this will be nice enough to make the alpha plus beta power appearing. That's the idea. And then in the end we have to take care of the prefactors. We will see this works. Okay, so going through the functional calculus, this is the same as the function z to the k divided by 1 plus z to the 2k applied to L. And now we have to make appearing alpha and beta. So now I put in what the V is. So the V is this function here. This is an H0 infinity function. In 0 it has a decay like z to the k. In infinity it has a decay like z 1 over z to the k. So it's an H0 infinity function. So just by the elementary calculus, if I multiply with this one, this is also an H0 infinity function. I can take these two functions together, and this gives me z to the k plus beta, and in the denominator I have 2k, 3k, 1 plus z to the 3k of L applied to U. Now, again in the elementary calculus, I can now, what I want to have is z alpha plus beta divided by 1 plus z to the 2k applied to U. This is the thing I want to have, where the alpha plus beta sum is there, and I need this to regularize it, to have enough regularization to make this an H0 infinity function. This is the regularizer for this one. So what remains here is a zk minus alpha divided by 1 plus z. And now note, this is also again an H0 infinity function to the k here. 1k is left, 2k here, 1k here. This is also an H0 infinity function. At 0, you have a decay. limit to 0 with this power, and in infinity the k is bigger than k minus alpha, and k minus has a bigger real part as k minus alpha, so you also have a decay. Okay. So I can take these apart like that. Of L. Huh? Okay, like that. One more. Okay. So, now this element I will call W. And now, where is this W? So I know that U is in the domain of L to the alpha plus beta. This means that if I multiply the underlying function with the corresponding regularizer, I'll end up in the range of the regularizer. So what we get is that W, so the function regularized applied of L applied to U must be in the range of the regularizer, so this is in the range of 1 plus L to the minus 2k. Again, this is a resolvent. Some power of the resolvent, this is the same as the domain of L to the 2k. So this function W is in the domain of L to the 2k. Now we've seen that the domain of L is invariant, so this was Corollary 517. If you are in the domain of L and you apply a functional calculus, so you apply some operator f of L, such that f of L is a bounded operator, and this is the case here, so this operator f of L here is a bounded operator because this is an H0 infinity function. In this case, the domain is invariant under this application. So if W is in the domain of L, then this operator applied to W is again in the domain of L. And so I have power of 2k, so I apply this result 2k times, and I get that this whole thing is in the domain of L to the power 2k. And so this is Corollary 517. That tells us that this whole element, so L times 1 plus L to the minus 1 to the k, 1 plus L to the minus k applied to V, all this thing is in the domain of L to the 2k. And now we have to go really long piece. We have to go back to the exercise 1.3, so into the very first lecture. In this very first lecture, in this exercise, it was shown that this operator here, so L times the resolvent, also leaves the domains invariant. So what we get is that 1 plus L to the minus kV is again in the domain of L to the 2k. So this is the point where we get again rid of our regularization. I had to put this regularization to make this calculation possible, because otherwise these parts wouldn't have been H0 infinity functions. But now I have to get rid of it, and this is this exercise 1.3 that tells me I can get rid of it, and I know that already this function, this part here, is in the domain of L to the 2k. Okay, and this now means this is a resolvent, so this means that V is in the domain of L to the k. Just apply k times the operator 1 plus L. Okay, and this was exactly what we had to prove. So we had to prove U is in the domain of L to the beta if and only if V is in the domain of L to the k. So this is what we wanted. Now you see there's some work to do to get the domains right, but we really have this this is a formula for the powers for all positive real parts. Okay, so and then there's a second claim of this proposition, which is about the domains of L to the alpha and L to the k and being a core. And in fact, I will not prove this special case, but I will prove even a more general result. So this B will be a special case of the following lemma. Where I replace the fractional power function by any regularizable function. So this claim in B here is just the special case for the fractional power of a really general result. And the general result is the following. And nevertheless, we formulated it like this because that is what we will need most of the time. So in later chapters, we will very often use this core, or sometimes use this core for the fractional power. So that was the idea to state it explicitly. But the result itself is more general. It tells you if you have any regularizable function, so we have a phi greater than the sectoriality angle, and you take any regularizable function in the functional calculus of L, then now we have again the two cases, L injective or not. So if 1 plus z to the minus k regularizes f, so you do not get it for every regularizable function, but you will see in the proof it depends very much on having these special regularizers, but every function that you can regularize with this one or with the injective one will get this result. So if this function regularizes f, as it does for the fractional power, then always the domain of L to the k is a core for the domain of f of L. And if you take f to be the fractional power function, this is exactly the first claim up there in 6.3b. And secondly, if the thing is injective, or if z plus 1 plus z to the minus 2 to the k regularizes f, then not only the domain, but the domain of L to the k intersected with the range of L to the k is a core for the domain of f of L. And if you plug in f being the fractional power, you get exactly b up there. And once we have proved this, this also shows that in all these cases f of L is densely defined. Why? Because while showing this, we will have to show that to be a core, so core means it's a subspace, the domain of L of k is a subspace of this space, and it's dense with respect to the graph norm here. That's what a core is by definition. So in particular, we will show that this domain of L to the k is in the domain of f of L, but we know from the second lecture, so this was proposition 2,4e, that these two sets are dense in H. So this means you have subset of domain of f of L that is dense in H, so this is also dense in H. So once we've proved this, we immediately get that f of L is densely defined. Okay. So we have to prove this result, and I will show you in detail the proof of A, and then proof of B is along the same lines. You have to work with the other regularizer. This changes some details, but I will just give you the hints of how to change it, because it's from the idea of proof is exactly the same. You just have to change the right details. So we'll do the proof of A, and this has two parts. Before talking about this domain of L to the K being dense in this one with respect to the graph norm, we first have to check that it's a subset. So the first thing to do will be that this domain is contained in this one. So this is part one. Domain of L to the K contained in domain of f of L. Okay, the only thing we know is that 1 plus z regularizes our function f. So let's call this, as usual, let's call this E. And then take some u in the domain of L to the power k. So how is this domain of L to the power k linked to this function? Now this function is a pth power of a resolvent. So again, this domain of L to the k is nothing else than the range of this function E. So the range of 1 plus L to the minus k, and this is the range of E of L. So we know we have taken our u in the domain of Lk, so as this domain is the range of E to the E of L, we can now pick some w in H such that u is the image of w under E of LW. And then it's just one short calculation. So what do we want to prove? We want to prove that u is in the domain of f of L. We have to think about what was the domain of such an operator f of L. It's all the elements of the Hilbert space H such that E times f of L applied to u is in the range of the regularizer. So this must be in the range of E of L. So let's check if this is in the range of E of L. So in the end we have to find that this is in the range of E of L, then we are done. Okay, what can we do about this? Plug in the definition of W. No, U. Yeah. Okay, so plug in the definition of U. So that's it. EF of L times E of LW. Now these are both functions coming from operators coming from functions in Dunford-Rees class. So everything here is bounded. We know that different f of L and f of g of L for different f and g commute. So this is the same as E of L, EF of LW. And now you see that this is in the range of E of L. Okay, it's in the range of E of L. And this means that U is in the domain of f of L. Okay, that was part one. And now part two, we have to show that it's not only a subset, but that it stands with respect to the graph norm. Okay, so what we do for this, we take our regularizer up there and put in an additional parameter. So I will denote this by ET. So this is the function 1 plus tz to the minus k for t positive. What is the idea? Why do I do this? Because this regularizer is nice because it puts us into the domain of L to the k. And so this also puts us in the domain of L to the k. This is just factor times a resolvent. And what happens now if you let t go to 0? This is again something to remind from lecture 2, from chapter 2. So this was again proposition 2.4. We will see proposition 2.4 several times today. if you let t go to 0, this approximates the identity. This is an approximate identity. And so the idea is to regularize your u with this operator, leaving you in domain of L of k, and then let t go to 0. This will converge to u. So you found something in the domain of L of k that converges to u. And the only thing that we have to make sure is that this convergence is good enough. Namely, it's not just convergence in H, but it's convergence in the domain of f of L, so with respect to the graph norm. So, but that's the idea. Okay, so we take this function et. Then, whatever you take as functions u in H, you will find that if you apply et of L to u, this is, now we have to plug in L here. This is a resolvent, so this was example 521 that told us that for resolvents the functional calculus gives what we want, what we expect. So this is 1 of TL, 1 plus TL to the minus k. U. And now this is 2 for D, proposition 2 for D, which tells us that if you let t go to 0, this goes to u. And as a limit in H. Okay. That's this approximate identity thing. Now, what we want to show is that domain of L to the k is a core of domain of f of L. So what we have to do is we have to take a u in this domain and approximate it by functions here. So we take a u in the domain of f of L. And then let's see what are the properties of such a u and of or et of Lu. So now we take this et of L applied to u. We know for every u in H, this will be in the domain of L to the k. This is just a kth power resolvent. Okay, so if we approximate u by such functions, we are fine because they are in the set that we want to show it's a core. Okay, first thing. And also note that we have already proved this is in the domain of f of L. This was step 1. So at the same time, we know that et of Lu is in this domain. We have already seen here for every u in H, so in particular for every u in the domain of L to the k, this converges to u in H. But this does not suffice. We need convergence in the graph norm. So we also have to prove that f of L applied to et of Lu, this has to converge to f of Lu. Once you have that, both summands in the graph norm converge, so then the graph norm also converges. So we have to show that this goes to f of Lu. And so the aim is to show this goes to f of Lu in H for t going to 0. Okay, why is that the case? So now we have a product. No, what we know in general is this product is contained in. So we want to make this an FET of Lu. Question is, why are we allowed to do it? This operator is a subset of this operator, but the point is, U is in the domain of f of L. So, and this is a no. This is just equal because et of L is a bounded operator. So this is 515. We had in theorem 515 we had that if the right operator of the product is a bounded one, then you get equality. There is no problem. So the next thing is to change this here. So this is etf of LU. And now I want to split this up again, and here it's the point to check, because if I split this up, now the right hand side operator is not a bounded one, but I know that U is in the domain of f of L. So I can put it into the product, and this gives Et of L f of LU. Okay, so this is again 515. I have in 515 I have an inclusion that this operator is contained in that one. No, that this operator is contained in that one. So the conclusion is this operator is contained in that one, but I know that U is in the domain of this operator. So the two are equal. So, and now again Et of L is an approximating identity in H. So this converges to f of LU in H. And everything's fine. Okay, so this was part A. And then for part B, as I said, you do more or less the same stuff. The same tricks and the same arguments, but for part B you have another regularizer, so you have to take another function E and other functions Et. So this is an analog argument. And what is still more or less obvious is what do you take as E? You take your new regularizer. So this is the right choice of E. And now you have to change the definition of Et to make the proof work. And then for this it's good to think about what did we need about E and Et to make the proof work. Okay, we needed that E and Et regularize our function, and that they map inside domain of L to the K. Here we have to make sure that they map into this one, because that is the one we want to show it's a core. So we have to make sure that E and Et map into this set. Okay, let's check for E. It maps into the domain of L of K, because there are two resolvents and one operator, so this is okay. Just heuristically, one has to check, but it works. And it also maps into the range of L to the K because of the Z here, of Z to the K. Okay, and now we have to make sure that the Et still maps into this domain intersected with range, and that it still is a approximate identity. Because if you have this, the proof will go through. That's the two things you needed for Et. It maps into the space here, and it's a approximate identity. And the right way to get this is the following function: 1 plus tz to the minus k, t to the minus 1z divided by 1 plus t to the minus 1z to the power k. This is not completely obvious, but convince yourself and check. If you take this Et, it has all the properties that you need. Okay. So this is what I want to show, more or less what I want to show about fractional powers at the moment. So we have defined them for every positive real part. We can calculate them with them as we are used to, and we have nice information about the domains. So we do not know precisely the domain for sure. This might be a complicated problem, but we have a core, which is already, if you have a core, this is good, because this is a dense subset in this space. So once you know things on the core, you know more or less what the operator does. And this core is the domain of L to the K, and this is easily accessible. Most of the times easily accessible, at least much easier accessible than the domain of some fractional power. Okay, there's one final remark. And that is, you might have wondered, what is about negative real parts, so z to the minus 1/2 or z to the minus 5. And what seems natural, this might work, but if L is not injective, there should be a problem. So if L is not injective, L to the minus 1 probably is not such a good idea. So that is why up to now all the powers had positive real part. But if you put in addition that L is injective, then it turns out that the function z to the alpha is regularizable for all complex exponents. Then you can also regularize the negative exponents, so the exponents with negative real part, because then you have polynomial control at 0 and infinity. And since it's injective, polynomial control at 0 and infinity is enough. And because you can use the other regularizer, so in this case you can define L to the alpha again as z to the alpha applied to L for all complex exponents. And then in the end of the last lecture we had this proposition 520, which told us what happens if you have two functions f and g such that f times g is 1. And if one of the two is injective, if f of L is injective, then g of L is injective too, and the two are inverses one to each other, and this is exactly the right thing to apply here. And it tells you that if L is injective, L to the alpha also is injective, and that L to the alpha to the minus 1 is just L to the minus alpha. So then you have really, in case of an injective operator L, you can calculate with the fractional powers as you are accustomed with, just like powers of functions or powers of z. Okay, so this is fractional powers, and I think this is a good moment before we continue with the other applications to make a short break, and we'll resume in 10 minutes. So let's start the second part. The next application of our functional calculus that I want to show you, I will just give you an idea. So this is more or less some explanations about an exercise. So the next subsection is about the exponential function and semigroups. And we invite you to do the details of everything that I do now in the exercises. So this is more an appetizer for these two exercises. We've seen in the Remark 5.3a, so this is a reminder, in Remark 5.3a we've seen that if the sectoriality angle of our sectorial operator is less than pi over 2, then the exponential function is even in our elementary calculus. So then we can define e to the minus tl by taking the exponential function e to the minus tz and plugging in the operator L. And this can be done for every positive t. This is because this function here then is even in the elementary calculus. Note this only works if phi is less than pi over 2. So we need a sectoriality angle that is less than pi over 2. And now we have this means we have an exponential function of our operator. And if you now think back to your classes in ordinary differential equations, you might have seen an exponential function of a matrix, so of a linear operator on a finite dimensional space. There, in ordinary differential equations, this exponential function is used to solve linear equations. And somehow now we could do the same. So the idea is, if you give an initial value in our Hilbert space H, and then you define the function u of t as E minus TL U0, then if everything works out nicely and if everything is as it should, then this should solve some differential equation of the form u prime of t plus lu of t equals 0 with initial value u of 0 is u0. So this is what is called an abstract Cauchy problem. It's a Cauchy problem from ODE, but formulated in some abstract Hilbert space H. So it's an abstract Cauchy problem. And this is not as abstract as it might seem. For instance, if you take a concrete operator, so if you take for L our negative Laplace operator with Dirichlet boundary condition, so with on some h10 of omega, then this abstract Cauchy problem, at least formally, corresponds to a well-known partial differential equation. That is, okay, we have a time derivative of u plus L, so minus Laplace of u equals 0, and u of tx equals u naught of x. And we have the Dirichlet boundary condition, so this is for t positive and x in omega. We have u of tx equals 0 for t positive and x in the boundary of omega. This is Dirichlet boundary condition. And we have the initial value u of 0x is u0 of x for x in omega. And this is the classical heat equation. So this corresponds to the heat equation, one of the most famous partial differential equations. So in some sense, this should give us a possibility on the abstract level by functional calculus to give a solution of the heat equation. And to other partial differential equations when there's not a Laplace here, but some sectorial operator L. And this works perfectly nice. There is a interesting, huge theory behind this. And as I said, you are invited to start with this theory in the exercises 3 and 4 to this lecture. And if you put everything together, what is shown there, and let me summarize this in some proposition, is the following. And then, as I said, there's a huge interesting theory behind this, and I'm rather sure that we will see some of this in the project phase to this internet seminar. So the result is, again, suppose that the sectoriality angle is less than pi over 2, otherwise this idea doesn't work. And then define e to the minus TL for t positive as above. This is called the holomorphic semigroup generated by minus L. Why it is called holomorphic, this is you see if you solve exercise 6.4. And why it is called semigroup, you see if I write down the first assertion of the proposition. So let's also take an u0 in h, some initial value. Then first thing, you have the usual law for the exponential functions. So e to the minus sl times e to the minus tl is the same as e to the minus s plus tl. And this is a semigroup law, so this is why it's called a semigroup. So this is the semigroup property. Secondly, you have so-called strong continuity at 0. So if you look at the limit t going to 0, e to the minus tl u0, then you get u0. So strong continuity in 0. In the language of our abstract Cauchy problem, this means that in this sense of a strong limit, this initial condition is fulfilled. So this initial condition means u of 0x, so this is e to the 0 L u0, so this is u0. Then we also get some information about the long time behavior of the semigroup. So if you look at the limit t to infinity of e to the minus t L u0, this gives you the long time behavior of the solution to the abstract Cauchy problem, then you get p u0, where p is some projection. P is a projection onto the kernel of L, but pay attention, it's not, in general, it's not a orthogonal projection, it's a projection onto the kernel of L along the closure of the range of L. We know from chapter 1 that, for chapter 2 for sectorial operators, that the Hilbert space H can be decomposed into the kernel plus the closure of the range, and the projection here is just the projection to the kernel along the range. So this is long time behavior of the solution, and the fourth assertion is that it is a solution, so the function t going to e to the minus tl, this is, if you look at it as a function from the interval 0 infinity to L of h without 0 here at the moment, then I claim this function is continuously differentiable, and the derivative is what you would expect and what is the right thing for our abstract Cauchy problem. So the derivative of e to the t minus tl is minus L e to the minus tl. And this also means this function e to the minus tl u0 solves the abstract Cauchy problem. As I said, this is an invitation to the exercise, and we will surely get back to this in the project phase. This idea of semigroups and of looking at abstract Cauchy problems in this way, in some sense, was the starting point of this whole endeavor and internet seminar. So the very first internet seminar in 1998 was about this topic. Yeah? So somehow this is back to the roots at this point. Okay, so this is the second application of our functional calculus that I want to show you. And now there is a third part of this chapter, which is about the so-called adjoint calculus. So what I will look now, we have a functional calculus for our sectorial operators L. We've seen that once you have an operator L that is sectorial, then the adjoint of this operator has the same property. It's also a sectorial operator, so you can also do a functional calculus for L star. And the obvious question is, are the other two calculi somehow interrelated? Yeah? Is there a relation between the calculus for L and for L star? And the first thing to make sure is that the adjoint really is exactly of the same, has exactly all the nice features of L. So this is the first lemma. I will show that if L is sectorial, then also L star is sectorial. And the angle is the same. So the sectoriality angle of L star is the same as the sectoriality angle of L. And we will also see that the property whether the operator is injective is maintained. So if you have an injective sectorial operator, the adjoint also is an injective sectorial operator. Okay. So this, once we have proved this, this means L star is as nice as L. So it might be worthful to check the interplay between the calculus for L and the calculus for L star. Okay, so the first thing to note, and somehow the key to note for all of this, is that we in the chapter 1 we have seen that the adjoint of the resolvent of a sectorial operator is given by the resolvent of the adjoint at the point lambda bar. So this was a formula we shown in chapter 1, and somehow from this you can read off everything, because the nice thing about sectors is that they are invariant under complex conjugation. So if lambda is in the sector of angle phi, lambda bar is in the sector of lambda s phi, if and only if lambda bar is in the same sector. So this we've also seen that once this resolvent exists, this resolvent exists, and everything fits together well. And now this means that once a lambda is in the sector outside the sector in the resolvent set of L, the corresponding lambda bar, which is then also outside the sector, is in the resolvent set of lambda L star. So you get that the spectrum of L and L star are in the same sector. And since also the norm of these two is the same, once you have an sectoriality estimate, so that the resolvent decays like 1 over modulus of L for this operator, you get it also for this one. So the sectoriality follows immediately. So from this and the fact that S phi is invariant under complex conjugation, it follows that also L star is sectorial. Sectorial means resolvent set is in the right exterior sector and resolvent estimates, and the sectoriality angle of L star is at least as good as the sectoriality angle of L. At the moment it still might be better, but it isn't, because we know that if you have a sectorial operator, its adjoint has the same nice qualities, so the adjoint of the adjoint also, but the adjoint of the adjoint is again the operator. So the sectoriality angle of L is the sectoriality angle of L star star, because that is L. And now we know that if we take away one star, we at most increase the sectoriality angle. Yeah, but this gives you the other inequality. So they are equal. Okay, so what remains to prove is that injectivity is maintained. So to prove this, assume from now on that L is injective. Then we know from, this was proposition 2 4b, I already told you there will be much proposition 2 today, that there is the topological decomposition of our Hilbert space H into the kernel of L plus the closure of the range of L. And now, since we supposed L to be injective, this kernel is not too big, it's just a zero set. So this is nothing else than the closure of the range of L. And then if you go back to the first chapter, so this was 120G, there was a link between the range of L and the kernel of L star. So the range of L closure is the orthogonal complement of the kernel of L star. This was 120G. Okay, so you know that the orthogonal complement for the kernel of L star is all of H. So kernel of L star is dense in H. So this implies that the kernel of L star is dense in H. But now kernels of linear operators are always closed. So this is a closed subset. And a closed subset of H that is dense in H, this means that it's all of H. And this means that L star is injective. Okay. So we've proved this first observation that somehow gives sense to the question, how are the functional calculi of L and L star related? Okay. And what we've seen here is already one sort of relation between the functional calculi. Yeah? If you take the function lambda minus z to the minus 1, this formula tells you that the adjoint of lambda minus z to the minus 1 in the L calculus is lambda bar minus z in the L star calculus to the minus 1. So it might that there seems to be some link. So how does this function? How do these two functions relate? This is the so-called holomorphic conjugate. So definition 6.8 is the following: is getting the right function f that you have to apply to L star to get the same as f of L. So again, we are on a sector with some angle phi, and we take some holomorphic function on this sector, and for this holomorphic function we define the so-called complex conjugate, and this is a function f star that is defined on the same sector, and that assigns to z the value f of z bar. So you plug in f z bar, and the result is conjugated again. Note this works because again the sector is invariant under complex conjugation. So if z is in S phi, z bar is in S phi, so I can put it into f. Okay, and this is called the complex holomorphic conjugate of f. And this will reappear now in the following result. Okay, that's the definition of the holomorphic conjugate. And before we work further with it, note that this function, if f is holomorphic, then f star also is a holomorphic function. This can be seen by several ways. For instance, the Morera theorem. You do the right path integrals along triangles, and you see that you can get it back to showing the same for the function f. And then you will see that f star is holomorphic. And second thing that is interesting for our functional calculus, if our function e is in the elementary calculus, so if it's in the Dunford-Rees class, then I claim f star also is in the Dunford-Rees class. Why is that? Okay, if f is the one function, f star is the one function it's in. If it's 1 over z, if it's 1 plus z to the minus 1, this is what we just calculated for resolvents, it's okay. And if this is h0 infinity, this means it decays at 0 and infinity, and if you have a function that decays at 0 and infinity, and you do the conjugates on the argument and on the function, this will not destroy these decays. So if you start in E, you remain in E. Okay. And what I want to show now, so the aim of what is coming now is to show that if you plug in L star in the functional calculus of f star, you end up with f of L star. So this is exactly what we have up there for the resolvent. If you plug in L star into f star, then you get the same as if you plug in L into f and then do the adjoint. So this is the aim, and naturally the main problem again will be to talk about domains. As long as f of L is a bounded thing, or as long as f is in the Dunford-Rees class, we will invest some work, and then this works. And in the general case, we have to be a little bit modest, and we will only show it for some special cases, but all the time this is our goal. So let's first put all the considerations about domain aside and start with the elementary calculus. So we take again some some angle greater than the sectoriality angle, and we only consider f in the Dunford-Rees class. And then the claim is this holds, so f star of L star is the same as f of L star. Okay. And what we do, we go through the three cases that you have in the Dunford-Rees class. The first two are simple. So what is if f is the one function? Okay, then f star also is the one function. Yeah? And this gives you identity equals identity. Okay, this is okay. Huh? Okay, second case, f is the resolvent, so 1 plus z to the minus 1. This is exactly what we have proved in chapter 1. This was the starting point of all the discussion. So this is also true. Okay, so what remains to prove is this equality if your function f is in h0 infinity, and then the nice thing is we can write down a Cauchy path integral to see what happens. So we, as usual, for the defining path integral for h0 infinity functions, I pick some angle greater than the sectoriality angle, less than pi, and then I want to look at the corresponding path integral, and for this it's important to note that the map, so the adjoint map, so that takes an operator and puts it, sends it to its adjoint, so as a map from L of h to L of h. This is an antilinear bounded map. So bounded in the sense of linear maps, of antilinear maps. It's an antilinear and bounded map. So the important point is we can take the results of our appendix and take this star, so this application of the star inside the path integral. Because it's a bounded operator, so you can put it inside the path integral. And that's what we will do. So we write down what is f of L star. F of L star. So we want to show this, so we write down the right hand side. This is given by the path integral, so 1 over 2 pi I integral over our path gamma psi, f of z, z minus L to the minus 1 dz. Star. So now we want to put the star inside inside here. What I will first do is put in the parametrization. So okay, this is a vector, I pull it out. Attention, this is a antilinear map, so this gives you a minus 1 over 2 pi I, because the I will give you a minus sign. Then I integrate over the real numbers, f of gamma of t times, okay, you get gamma prime of t from the parametrization, and then you have gamma of t minus L to the minus 1 dt, and then you have to do the adjoint. Now, as doing the adjoint is a bounded antilinear operator, this is appendix A13, I can take the star inside the integral. Okay, what happens if I have the star here? This and this are complex factors, so they come out with the bar. So this is minus 1 over 2 pi I integral over r, f of gamma of t bar, gamma prime of t bar. And what happens here? Now the nice thing is this is a resolvent. This is a resolvent, so we know what happens if we star this one. This is again the formula up there. If you star a resolvent, this gives you the resolvent of the starred operator at the complex conjugate parameter. So this gives you gamma of t bar minus L star to the minus 1. So this is again the second case. This is again the case for resolvents. Okay, so now let's use the definition of the complex conjugate. Here, this is f of gamma t bar, so this is f complex conjugate at gamma of t bar. If you calculate this gives you f of gamma bar bar, so f of gamma conjugate. So this is the same. And the second thing that you have to keep in mind now is that we exactly know what happens with gamma of t if you do a complex conjugate. So what was this path gamma of t? It was like that. So this is the angle psi, and this path is just going along the boundary of the sector with angle psi. And if you now do a complex conjugate, this just gives you the inverted path, so the path going backwards. So the complex conjugate, so this is gamma, and if you take gamma bar, this just gives you going back. Okay, this means gamma of t bar is just minus gamma of t. Gamma of minus t, it's just gamma of minus t. So this gives you integral over r f star of gamma of minus t times gamma prime of minus t times gamma of minus t minus L star to the minus 1 dt. Okay, now there's one substitution left to do. Just substitute s equals minus t. This gives you an s here, s ds, and a minus sign from the substitution, which kills this one. So you end up with 1 over 2 pi I integral over r f star of gamma of s, gamma prime of s, gamma of s minus L star to the minus 1 ds. And this is nothing else as f star of L star. Note f star also is an H0 infinity function, so this is all well defined. And what we've proved is the equality we want to have. Okay, so this is the easy case where there are no domains involved, where every operator is bounded. So now we want to extend this. If everything would be perfectly nice, we would want to extend this to our algebra of regularizable functions. You will see in the proof that I will show now that I will not show now, but you will see in the proof, if you look at it, that doing that this proof does not really work through for every regularizable function, because in the proof you need special properties of our usual regularizers, 1 plus z to the minus 1 and z times 1 plus z to the minus 2. And there are issues why you need these. So you only get a partial result, and the following is the partial result. So proposition 610. Again, we take some phi bigger than the sectoriality angle, and we take some holomorphic function on the sector. And now I will not give you a result for general regularizable function, but for functions that can be regularized by our special regularizers. So again, we have two cases. The L is not the L is injective, and the general case. So if f has a polynomial limit at 0 and polynomial control at infinity, so this is the case when you can regularize with 1 plus z to the minus 1, or some power of this regularizer. Or B, if L is if L is injective, L is injective, and F has polynomial control at 0 and at infinity, then you can regularize by our second usual regularizer z over 1 plus z squared. In these two cases, then the formula we want to have holds again true, so f star of L star is the same of as f of L star, even with equality of domains. Okay, as I said, I will not give the proof here, it's in the lecture notes, but for time reasons we have to skip this here. It's a rather, it's not a really long argument, but if you go through it, you will see there are some subtleties, and as usual, they are all connected with talking about domains. Let me write down one corollary of this for the special case of functions that we considered already in this course, so the fractional powers. And for this, let me just look at real exponents, so real positive exponents. For real positive exponents, I claim that the adjoint of L to the alpha is nothing else as the adjoint of L to the alpha. So for real positive exponents, you can exchange adjoints and put and the power. And the proof is now 2 lines. What is, if you take f equals z to the alpha, then what is f star of z in this case? You have to do z bar to the alpha bar, but these two, as this alpha is a real one, these two cancel out, so f star of z is just f of z. So that's why I only look at real exponents. For complex exponents this is false, but this is for real exponents, this works fine. And then this means that L to the alpha star is nothing else than f of L star. So this is f star of L star by our result up there, because this one is regular, has a polynomial limit at 0 and polynomial control at infinity. So it fits into this proposition. So f star and f is the same, so this is f of L star and this is L star to the alpha. Okay, so we know at least for real positive exponents you can exchange star and the power. Okay, so that was for the adjoint calculus, and there is now one application of our functional calculus left in this lecture, or in this chapter, and this will be a little bit a longer story, because it is a long story. We'll see there's also some historical background here, and this is about the so-called second representation theorem of Kato. So it's Kato's second representation theorem. And in today's lecture I will start to give you this theorem. I will prove it because it has with our tools now it has a rather short proof. And then today, and especially on Wednesday, we will talk about what does this theorem mean and why it's interesting. So the theorem was proved by Toshio Kato in the beginning of the 60s, and as the headline claims, it's called second representation theorem. And what we do again here is we go back to the setting of our lecture 2, so we look again at forms and operators coming from forms. So for this and the rest of this chapter, let me take another Hilbert space V that is densely and continuously embedded into our Hilbert space H. So think again of L2 and H10 or something like that. So in a Hilbert space that is densely embedded into our H. And then we consider a really nice form. So form A from V times V to C, and this now has more or less all the nice features that it can have if we look back to our section lecture 2. So we want to be bounded, accretive, elliptic, and symmetric. So the nicest form you can think of, and symmetric sesquilinear form. And we've seen that whenever you have such a form, this comes with an associated operator or with two associated operators. So by L, I will now denote the associated operator to this form. And since the form is symmetric, this operator will be a self-adjoint one. Self-adjoint operator in H. Okay. And the claim of this theorem is that however what this operator looks like, it just comes from a bounded accretive elliptic and symmetric sesquilinear form. Then I immediately know what the domain of its square root is. So by square root of L, I will denote L to the 1/2. This is, and L to 1/2 is well defined by our functional calculus. And but the functional calculus doesn't tell us anything about domains. It just tells you there is some domain. It's all the U such that EF of LU is in the range of the regularizer. Some domain. But Katos tells you if the operator comes from a symmetric, nice form and is self-adjoint, then you know what this domain is, and it's exactly V. It's exactly the form domain. And you even have a link between the square root of L and the form, saying that AUV is the same as the H scalar product of square root of LU, square root of LV. With equality here for all U and V in V. And both sides are defined on V, so this is fine. And this is also why it is called representation theorem, because what somehow is written here is that the form is represented by the operator square root of L via the H scalar product. So you can rewrite the form using the H scalar product by introducing this operator square root of L. And the proof is, it's not that long, because everything is nice here. So we first start this proof for the special case that U and V are in the domain of L. And then later on we will get it to the domain of square root of L, so to V with the density argument. But let's first do the calculation with U and V in the domain. Then you can just do the following. A of UV, since U and V are in the domain, this can be represented by the whole operator L. So this is the scalar product of L, U, and V. This is just the definition of L. Now, by 6.3, this was our lemma that told us that for fractional powers you have the usual calculation rules. You can split this L up into two square roots of L. So this is square root of L, U, V. Now, you can take the adjoint to the other side. So this is square root of L adjoint V. But now, the square root of L is in particular a fractional power, and it's a fractional power with a real exponent. So we know that the fractional power of the adjoint and the adjoint of the fractional power is the same, so I can take this star and take it under the square root. But if the star is under the square root, there is L star, and L is self-adjoint. So this is not there. And this is this formula for all U and V in the domain. Note, this only works for the domain because we went via the operator L here, and this only works if it's in the domain. So we have to do some density argument. And for this, look at the norms. So if you take the norm Lu, square root of Lu plus u plus norm of u, and I do squares here for making the calculation easier, then using, so for this is also for all u in the domain of L. So square root of Lu in norm is just this one where you put v equal to u. Huh? This is just square root of Lu, square root of Lu. This is this one. So you can rewrite this by the form. So, and this is the quadratic form, a of u plus the norm of u squared. Now use that a is a bounded form. So you can estimate this one by some constant times the v norm of u squared plus the h norm of u squared. Now you know, so this is because a is bounded. Now we know that a is elliptic. This gives you the other estimate. Elliptic means that the real part of a can be estimated from below by this one times a constant. So this is less or equal real part of a of u plus u squared. Now this is a symmetric form. So the quadratic form is real. So this real part of something real is not there. So, and now you can go back. A of u is again the square root. So this is the norm of the square root of u squared plus norm of u squared. And what you now find is that the norm on v and the graph norm of the square root, they are equivalent. So this is the norm on the space v. Oh, it's it's equivalent to the norm on v. And this is the graph norm of square root of L. So it's better to, So this is the right way to write it down. So now the norm of v and the graph norm of square root of L, they are equivalent. And if you now put together what that means, this is, so the norm on v and the graph norm of square root of L are equivalent. They are equivalent norms on the domain of L. All this calculation was for you in the domain of L. So this we know, but we also know that the domain of L is dense in V. This we showed in proposition 223. Whenever you have a sectorial operator, it's coming from a form, its domain is dense in the form domain. And this is with respect to the V norm. And on the other hand, you know that the domain of L is dense in the domain of the square root of L with respect to the graph norm. And this was 6.3. This was we showed there that once you have a fractional power, here the power is 1/2, and you take a k that is bigger than is bigger than the real part of this power, so take 1. 1 is bigger than 1/2. Then the domain of L to the k, so domain of L, is a core for this one. And being a core meaning dense with respect to the graph norm. So this set domain of L is dense in V, is dense in the graph norm, and you have this equivalence of the two norms on the domain, and now you can lift it by density, and you get. So this domain of L is now with is dense in these two spaces, and the norms are equivalent. So the closure of the two norms are the same. So this is the same as this, and you also get this equality here for all uv in the domain in V, or in the domain of square root of L, which is the same. So this is the Kato second representation theorem of Kato, and we will see in the next lecture on Wednesday why this is a really beautiful and nice theorem, and why Cato started to look at these things, and how this produced a question, a conjecture that kept mathematicians busy for many, many years, and which we will discuss at length during this internet seminar. So much for today. Thank you for listening, and we will be back on Wednesday.